In this video, I want to go through Boolean algebra, and I'm going to start with the table. Let's start putting A, B, not A and B, A or B, and A exclusive or B. Was right here. Okay, let's try to make it 0, 3. Oops, not work. Okay. Zero, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, and 0, 1, 1, 0. This is Boolean algebra. Okay, what it basically means? It means for example, in the first row, that's the first row, that's the second, third, and the fourth. In the first row, A, value of A is 0, the value of B is 0, and this is not A. So if A is 0, not A will be the opposite, not A will be 1. A and B is when they are like a intersection, like concatenation of both. A is 0 and B is 0, therefore the output of it will be 0. In this case, now is A or B. A is 0 and B is 0, therefore because both of them are 0, the output will be 0. And A exclusive or B, we will see that later, that in this case both of them has to have the same output, and we will go through it later, because this is right now just a table I want you to show you, and this is the table that we wanna see now, all the examples on it. This case will be the same. The value of is 0 from A, the value of B is 1, then not A will be 1, and if we see, for example, here is A is 1, so not A, not 1 is 0, that's why it's 0 here, right? This case the same, the value of A is 1, not A is 0, because it was 1, so not 1 is 0, right? What else to check with here? A and B, for example, here, A and B in here, in the row number 3. A is 1 and B is 0. But this, in order to be done, both of them has to be true, or both of them has to be false in order to be, no, not really, just both of them has to be true, which is 1, otherwise it will be 0. For example, the value of A is 1 and the value of B is 0. Therefore, because both of them are not having the same, then the output is 0. If both of them will be 0, there's not any example. Yeah, here on top there is a sample. If both of them are 0, this is also 0, but in order to be 1, both of them has to be 1. Okay, this is just the introduction of more or less what we're going to see with the Boolean algebra. Okay, so what is a Boolean algebra? Boolean algebra, Boolean Algebra is a mathematical system for reasoning to logical values, It describes condition and decisions using variables, operators, expressions, and laws. Okay. So binary number systems answer how is a value represented? How is a value represented? Boolean logic answer. Boolean logic answer. What decision should be produced? What decision should be produced from the current condition, the symbol 0 and 1 can represent numeric quantities, but in Boolean logic they are often interpreted as false and true. Okay. From representation to decision. From representation to decision. Let's say from hardware to a logical decision. There is a physical signal. It can be a voltage or a switch. Go to binary state. Zero or 1 to Boolean meaning. False or true. to decision, which is action or no action. Okay, it is important to know that a computer does not skip these layers. Which is the same as about physical state, bit, logical interpretation, and output. Okay. Okay, let's try to see this before we start. A Boolean variable is a variable that can have exactly one of two logical values. False or true. The values are commonly written as false or true. F, T, or 0, 1. In digital logic, 0 usually represents false and 1 usually represents true. And this is a convention of interpretation, not a claim that truth is physically made of the number 1. Okay. For example, we can say if door closed equal 1, the statement the door is closed is currently true. If door closed equals 0, then it is false. Okay. Do not assume, do not assume that one always means electrical power is present in logic. One means the defined condition is to the physical voltage convention is a separate layer, is a separate layer. Okay. Position, conditions, and predicates. So we see that. Okay, let's go through it. A preposition is a statement that can be classified as either true or false. Boolean algebra works with statements that have definite logical values. The hot is close, can be true or false at a particular moment, at a particular moment. Close the hatch is a command. So it's not itself a proposition. In software, comparisons such as temperature, greater than 80, or password equal to stored password produce Boolean values. Produce Boolean values. in hardware. Sensors and comparisons. Circuits can produce equivalent yes, no signals. Okay, if we see an example of this, we can say let age mean the hatch is closed and P mean the pilot is present. The sentence the hatch is closed and pilot is present becomes H and P. Okay, let's check the truth tables. Truth table. A truth table lists every possible input combination and the output by a Boolean expression or logic circuit. Okay, let's say for n independent Boolean, input a complete truth table has two power n rows. One input gives two rows. Two inputs gives 4 rows. Three inputs gives 8 rows, and 4 inputs gives 16 rows. So we can say number of inputs rows required and reason. Let's put 1, 2, 3, and 4. And here will be 2, 4, 8, and 16. Because it will be 2 rows per 1 input. Now it's 2 power of 2 because of the input, 2 power of 3, and 2 power of 4. That's the reason for every input there will be 2 rows. So for 2 rows it will be 4 because 2 for 2, then 2 times 2 times 2, 2 times 2 times 2 times 2. 2 input, 2 input, 2 input, 1 input, another one, and 4 inputs, which is the total of 16 rows required. This is how we create the tables. I'm gonna put this on charts. Is it turning out? Oops. Let's bring it back. Is it back? Okay. That was quick. Didn't need enough time to charge it back. Okay. I'm gonna skip now. Okay. Let's say not logical inversion. Not reverses a Boolean value. So true becomes false, and false becomes true. Not is a unary operator because it acts on one input common notation are not common notations are not A, represented like this, A and this square bracket. This quotation mark, this quotation mark, A quotation mark. Okay. So for example, if A means alarm active, then not A means alarm not active. Let's put A and not A. Let's put 0 and 1. Then if A is 0, not A will be 1, and if A is 1, then not A will be 0. So row output is always the opposite of input. Okay. Let's see and let's put it like all required conditions. Let's say that and produce true only when every input is true. And is useful. This is still recording because it went off. I'm not sure now. Yeah, it's fine. Okay. When several requirements must be satisfied. Simultaneously. For two inputs, A and B, the output A and B is 1 only where A is equal 1 and B is equal 1. Then common notation are A and B. A, don't say this is B, or simply AB. As an example, a launch permission requiring both power OK and hatch shell is L is equal to P and H, which will be launch is equal to power and hatch. That will be the common notation of launch, power K and heat shield. Okay. Can put here A, B, and A and B. 0, 0, 1, 1, 0, 1, 0, 1. Okay, so A is 0 and B is 0, then A and B will be 0. Because A is 0 and B is 1, they are not the same, because both has to be 1 in order for A and B to be 1, then this is also 0. And here, because A is 1 but B is 0, is also 0. But here A is 1 and B is 1, so A and B is equal to 1. Okay, so we can say that all requirements must be true. Okay. Let's check or, which is at least one condition or produces true when at least one input is true. One input is true. Boolean or is inclusive is true when A is true, when B is true, and also when both are true. This differs from the exclusive, meaning sometimes implied by everyday language. Common notation are A or B, and A plus B. For example, an alarm may activate when smoke is detected or temperature is too high. Alarm equal S or T. The alarm will be variable, and then the shortest will be S from smoke or T for temperature. Okay. Let's put A, B, A or B. 0, 0, 1, 1, 0, 1, 0, 1. Okay, and the first one is A is 0 and B is 0, and this has to be A or B because both of them are 0. This is 0. Here, A in the second row, A is 0, but B is 1. Because it has to be A or B, it will be activated anyway, so it will be 1. And then here we have the same, but with A in this case, because in the third row we see that A is 1 and B is 0, but doesn't matter that B is 0 because it has to be one of them, right? Because A is 1, then A or B will be 1 because of A. And then because A and B in the last row are 1, A or B will be 1 because it can be also if both of them are 1. So we can say that 1, let's put here because my face will be there, 1 or more true inputs are enough. Or at least 1. Okay. Let's say XOR exclusive or exactly one of two inputs. Okay, exclusive OR, which is exclusive OR, produces true when it's two inputs are different. For two inputs, exclusive OR is true when exactly one input is true. If both are 0 or both are 1, the output is 0. Exclusive OR is central to binary addition because the sum bit of two input bits is 1 when the bits differ. Common notation are A XOR exclusive OR B and A plus encircle B. For example, a two-way status indicator can turn on when switch A and switch B are in different position. Okay. Let's do A, B, and A exclusive or B. 0, 0, 1, 1, 0, 1, 0, 1. Okay, in the first row we have A is 0 and B is 0, so A exclusive or B will be 0 because if both of them are the same, then the output is 0. In this case, A is 0 but B is 1. Because one of them is 1, then A exclusive or B will be also 1. In this case, we have the same with A in this case because A is 1 and b is 0, then a exclusive for b will be 1. And here both of them are 1. In the normal OR, this output would be 1, but in exclusive OR, every time a and b are the same, then in this case it will be 0, because we are only looking for one of them. So we can say if they are different, then it will be 1. If they are the same, it will be 0. Okay, none, not of an. Okay, so none, which is not an, produces the opposite of an. It is false only when every input is true. The name combines not and an. First, imagine the AND result, then invert it. None is especially important because any Boolean function can be built using only NAND gates. For A equal 1 and B equal 1 and gives 1, so none gives 0. In every other row, and gives 0, so none gives 1. So always the opposite. A, B, and none. 0 0 1 1, 0 1 0 1. Okay, and we know already it will be 0 0 0 and 1, right? And now this is just basically the opposite. If this is the result of AND, because we know that in order for AND to be done, both of them has to be the same result, right? And in this case, only the last row has the same result, so that's the only one working for AND. And for NAND, we just know there is not AND, which is the opposite. So then will be 1 1 1, and here 0. Okay, so NAND is equal to not A and B. Okay, let's see, not, which is not of or, not produces the opposite of or. It is true only when every input is false. The name combines not and or. So first evaluate or, then invert it. Nor is also a universal operator. All Boolean functions can be constructed using only NOR gates. As an example, if neither primary control nor backup control is active, nor can detect the no control source active condition. Okay, if neither primary control nor backup control is active, nor can detect the no control source active conditions. It is true only when every input is false. Okay, so for primary control, the result is 0, and for the backup control also the result is 0, okay, if both of them are 0, then NOR, which is the opposite, because with all, one of them or both of them has to be true. Only one is enough. But if both of them are 0, then NOR is detect this and not control source active condition. So in this case, it is true because both input are false. Okay. A, B, or NOR. 0, 0, 1, 1. More or less the same. Change much. 0, 1, 0. Okay, in this case, A and B are 0, so all could be 0. A is 0 and B is 1. One of them is 1, so in this case it's 1 because B is 1. And here we have the same, A is 1, so that will be 1. And in order if both of them are 1, then it is 1 too. Okay? What happened with NOR, as we saw in the example before, if both of the output input are false, are 0, then the output then will be 1, because it is only true when both inputs are false. So in this case will be false. In this case A is 1, so also will be false. And in this case, because both are true, then it also will be false. So NOR is equal to not A or B. Okay. Next, NOR exclusive NOR equality of two inputs. Okay. So exclusive NOR produces true when its two inputs are equal. Okay. Exclusive NOR is the inversion of exclusive OR. It output one, 4, 0, 0 and 1, 1 and 0, 4, 0, 1 and 1, 0. It's understandable, right? Only when the inputs are equal is when the condition is 1, but if the inputs are not equal, like 0, 1 or 1, 0, then the output is 0. This makes it useful as a 1 bit equality comparator. Okay, for example, to test whether I receive bit are matches, am I able to write today? Matches unexpected bit E is match equal R exclusive NOR E. Okay, to test whether a received bit R matches unexpected bit E, use match equal R exclusive NOR E. Okay, so for example, in this case, the bit R is 1, and then the bit E is also 1, then both of them matches because, as we saw above, it outputs 1 if the outputs are equal, right? If the inputs are equal, for example, for 0 0 and 1 1. In this case, if R is 0 and E is 0, then it will be true, and if R is 1 and E is 1, will also be 1. It will be true. Let's have a look. A, B, exclusive or unexclusive NOR. 0 0 1 1 0 1 0 1. Okay, for exclusive or, we knew the only one of them has to they have to be different and only to be true. For example, this one will be false and this one will be false, but this one and this one will be true because in here both of them are 1 and it has to be different. They have to be different. So in here will be 0 and here will be 0 and these two will be 1. Exclusive NOR is basically the opposite, only when they have the same input then it's true. Okay, so same is 1, different 0. Okay, let's put this some theory. If we come across exercises like this, then we know operator precedence and parentheses. operator, precedent, is the grid, order used to evaluate a Boolean expression when parentheses do not specify the order. A common precedent order is parentheses first, then not, then and, then or, exclusive or is often placed near or, but conventions vary between programming languages and textbooks. Parentheses removes ambiguity and should be used generously. Okay. So not A and B normally means not A and B, not A and B. These expressions can produce different outputs. So recommended evaluation order one is parentheses, two is not, three and or none, 4 exclusive or exclusive not and 5 or not or. And as a rule, use parentheses when meaning could be unclear. Okay. Boolean expressions. A Boolean expression combines Boolean variables, constants, and operators to produce one Boolean result. Okay. Expressions are models of decision rules. Each intermediate operation produces a Boolean value that becomes an input to the next operation. Expressions are models of decision rules. Each intermediate operation produces a Boolean value that becomes an input to the next operation. For example, f it's equal to to a and b. G is equal to a or not b. H is equal a exclusive or b and c. Okay, let's see examples. Let B is equal a pilot present H equal hatch sealed and E equal emergency override. A possible permission row is L equal to P and H or E. Okay, so P is pilot, L will be for launch. So launch is equal to pilot and hatch seal. This condition has to be done, or E, emergency override. Okay, we got it right. So we got launch will be done only if the pilot and the hatch seal is both of them true, or if the emergency override is true. Okay. Okay, we have a table here. Let me have a look on this table. Okay, let's copy this table. A, B, C, A, and B, not C and F. Zero, 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 one, 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 one. It's difficult to catch it. Okay. We have 0, 0, 1, 1, 0, 0, 1, 1, and in C we have 0, 1, 0, 1, 0, 1, 0, 1. Okay, let's try to do A and B. We already know that for the and, both of them has to be, or three of them. But I'm not sure if we can do majority in here. Can we do majority in here? Oh, sorry, it's A and B, not C here. Okay, never mind. Okay, for A and B. A is 0 and B is 0, so A and B in this case is 0, right? Because for and we know that both of them has to be true in order for B true. So 0 and 0 is 0 for the third row. 0 and 1, unfortunately, A is not true, so it will be still 0. And here, still 0, 1, 0, 0, 1, 0, 0. And here, both of them 1. So 1 and both of them 1. So 1. Okay, for not C. Not C is just the opposite, right? So 1, 0, 1, 0, 1, 0, 1, 0. I was just doing the opposite of this, the opposite of this, the opposite of this. Okay? Just the opposite of C. And then we have F, but F will be, F is equal to A and B, or not C. Okay? Okay, so A and B, in this case, A and B is 0, and not C is 1, so F is equal to 1, because A and B, or not C, A and B is 0. You already saw it in here, right? So it's 0, but not C is 1, because C is 0, so not C is 1, which is the opposite of C. And then in this case, then F is 1, because in here F is A and B, or not C. Because C was 0 and not C is 1, then F is 1. Okay, here we have also 0 in B, but in not C we have 0. So in this case we have 0, because none of them are true. In here we have A and B 0, but not C is 1, so F is 1 also in here. And here we have A and B 0, but not C is also 0, so that will be 0. A and B again is 0, but not C is 1, so that will be 1. A and B 0 and not C is 0, so it's 0. A and B is 1 and not C is 1. Both of them are true, so in OR we know that doesn't need to be 1. If both of them are true, then it's also true. And in here we have A and B is 1, but not C is 0. It is also true, because this condition is not getting done, but this one is getting done, so that make it true. Okay, let me double check if I did it right. I don't want to give you any inaccuracy. I'll put 1 0 1. That's correct. 0 1 0 1 1 0 1 0 1 1. That's correct. Yeah. Okay. Okay. Reading a Boolean expression in words. To read a Boolean expression, identify the outermost operator, then describe each of its inputs. sub-expressions. Okay, for f equal to a and b, or not c, the outermost operator is or. Its left input is a and b. Its right input is not c. Okay, so that's the outermost operator. On the left we have a and b, and on the right we have not c. So this expression tree, yeah, let's do it this in a blank one. Okay, this expression tree way of thinking is the same principle used later when drawing a circuit. F is true when either both A and B are true, or C is false. Okay, the example that we saw before, A and B, or not C. Okay, so for F equal to A and B, or the outermost, not C. So the outermost again, or then on the left we have an. On the right we have not, and give us A and B, and not gives C. So that's the expression 3. Okay. Let's see the Boolean laws. Boolean laws. This is the, hopefully gonna fit in the algebraic toolkit. This table we need to have it dissolved, is a must. So Boolean laws allow an expression to be rewritten without changing its truth table. They are used to prove equivalence, simplify logic, and reduce circuit complexity. Law. Let's try to make that already, otherwise I'm not sure if I'm gonna be able to do it. Okay. Let's put identity. Okay. Domination. No. Idempotent. Idempotent. Complement. Hopefully it can be readable in evolution. Commutative. Associative. Distributive. Absorption. And the Morgan. Or form. And form. Okay. A plus 0 is equal to A. You don't need to memorize this table right now, just have it, and then with the examples that we will see later, because then we will go through every single one of the laws down here on the left, and it's good to know how we will present it, those form in or an arm in or an. So don't worry if you really don't understand it now, because by By the end of the video, you will do a plus 1 equal 1, a plus a equal a plus a not equal 1. So a plus 0, a plus 1. Okay, the phone got off. Where will we? What exactly are we doing? Okay, I'm gonna try to catch up later with this. So what I was explaining is that in this case, for example, in complement, this is recorded too. Yeah, okay. In complement, this is a or a not equal 1. I'm gonna give them a not equal a plus b equal b plus a plus b. This is in associative a plus b plus c equal to a plus b plus c. A plus bc is equal to a plus b. Oops. We will in distributive and distributive bc equal to a plus b and a plus c. In abstraction is a plus ab equal a, and in the Morgan is a plus b not equal a not and b not. Okay, in form is a and 1 equal a 0 equal 0, a equal a a not equal 0, a b equal ba a b c equal a b c a b plus c equal a b plus a c a plus b equal a and a b not equal a not plus b not. Okay, so notation used on this page plus means or doesn't say doesn't say or means an apostrophe. It is called apostrophe. I thought it was called quotation mark. An apostrophe means not. My bad, I guess. Those A means not. A. Not A. Okay. So we can start. Okay. Identity and domination laws. Identity and domination laws. Identity laws leave variable unchanged. Domination laws force the result to a constant. Okay. Identity A or 0 equal to A because adding a false alternative changes nothing. A and 1 equal A because requiring a condition that it is always true changes nothing. Okay, identity A or 0 is equal to A because adding a false alternative changes nothing. A and 1 is equal A because requiring a condition that is always true changes nothing. Okay, domination. A or 1 equal to 1 because at least one input is already true. a and 0 is equal to 0 because 1 required input is already false. Okay. If enable is equal p and 1, then enable equal p. If fault equal a or 1, then fault is permanently 1. Is understandable? If enable is p and 1, then we already know that 1 is about to be true because 1 is true, and enable is just p, so enable p. Because both of them are true, p is enabled and 1 is true, so enable p. And the same here. Then false is permanently 1 because false is e or 1. 1 is already true and e is false, so permanently is false is permanently 1. Okay. Can we check this? A plus. Okay. Idempotent complement. And double negation laws. And double idempotent laws remove repeated identical conditions. Complement laws combine a condition with its opposite. Double negation restores the original value. A or A is equal to A and A is equal to A because repeating the same condition adds no new information. A or not A equal 1 because one of them must be true. A and not A equal 0 because they cannot both be true. Not A equal A because two inversions cancel. Okay, so A or A equal A and A equal A because repeating the same condition adds no new information, and A or not A equal to 1 because one of them must be true. Okay, A or not A isn't there and not A. Okay, one of them must be true. A and not A equals 0 because they cannot both be true. Okay, because not A is literally not A, and both of them should be true. So this will be A and A, but because it's A and not A, they cannot match, and for that reason they cannot be true because both cannot be true. And the last one, two inversions cancel. Okay. So if we write it like this, we can keep it A plus A is equal to A and A is equal to A plus A naught is equal 1, A and A naught is equal 0, and A naught is equal A. Okay. Commutative and associative laws. Commutative laws allow input to swap order Associative laws allow regrouping of the same operator. Okay. A or B equal B or A, and A and B equal B and A. So the order of inputs does not change the output. A or B or C equal to A or B or C, and A and B and C equal to A and B and C. When the operator is the same, grouping does not change the result. So A or B is equal to B, or A and B is equal to B. Is equal to B and A. Okay, it's equal to B and A. Okay, because they are only using and the order of input does not change the output because it's just the union of both of them. Doesn't matter if you change the position. If A is 1 and B is 1 and you need both of them to be 1, doesn't matter if you put B one position or a different position. A or B or C is equal to A or B or C. Okay, so A or B or C is equal to A or B or C. Okay, just basically doesn't matter in which order we're going to do because we are not changing the result if we are using the same operator. In this case is or, doesn't matter if this is here or if this is here, if these two doesn't matter because we only need one or another one to be done in order to be true. Okay. Distributive laws. distributive laws. Expand or factor Boolean expressions. While preserving their truth table. So and distributes over or in the familiar looking form A B plus C equal A B plus AC. Boolean algebra also has the dual form A plus BC equal A plus B and A plus C. This second form may looking as well. Because ordinary arithmetic does not have the same dual law. So and distributes over or in the familiar looking form A and B or C equal to AB or AC. Okay, this will be A and B or C equal to A and B or A and C. Okay. Let's try to see more clear. Over or A B plus C equal to A B plus A C and or over and will be A plus BC equal to A plus B and A plus C. Okay, so we have an over or, which is A and B or C, which is equal A and B or A and C. And in the or over and, it will be A or BC is equal to A or B and A or C. Okay. Absorption loss. Absorption loss. Remove a more specific term. When a product term already determines the output. So A plus AB is equal A if A is already true, the OR result is true. If A is false, AB is also false. Therefore, AB contributes nothing. And then we have A and A or B equal A if A is false, then and result is false. If A is true, A plus B is true. Therefore, the larger expression reduces to A because A is already inside and A plus B. If this is A plus B is equal A. If A is false, then the AND result is false. This is the AND result is false. If A is true, A plus B is true. Therefore, the larger expression reduces to A. Okay. Can we check this example? Simplifies to alarm F. Okay. be like more confused. Let's go to the Morgan's law. We could see that in the next video. Morgan's law. The Morgan's laws explain how knot moves through and or. The operator changes and every input is inverted. First law, not A or B is equal to not A and not B. For a NOR expression to be false, both inputs must be false. Okay. And second law, not A and B equal to not A or not B. So for an expression to be false, at least one input must be false. Okay. First law, not A or B is equal to not A and not B. For an expression to be false, both of inputs must be false. Okay, and the second law is not A and B is equal to not A or not B. Okay. let's check the table so we can have it. We have A, B, not A or B, and not A and not B. Zero, zero, one, one, and 0, 1, 0, 1. Okay, so A or B. Okay, because none of the normal or A or B is done, because if this would be a normal or, it will be 0, but because it's not, it's 1. And in this case, in normal or this will be true, so it's false. In normal or is 1 will be true because of the not is false, and this is true in normal or, but because it's not also is false. So not A and not B. So basically the opposite of 10. 1 and 1 will be 1, and 0 and 1. In the AND condition, the requirement is that both of them has to be true. And in this case, it's not A and not B, so it will be, in here it will be 1, and here it will be 0. But still they're not the same, so it will be 0, and here it will be 0, and here it will be 1. Still, and here will be 0, and here will be 0, so it's also 0. Okay. Okay, we can check Mintro on this show. Okay, let's check the sum of products and Minterms. A sum of products derivation sub sum of products expression or together product terms. Each product term is an n of variables or their complements. Okay. A minterm is a product term contains every input variable exactly once. Either complemented this is starting me for too long, that's what happens. So either complemented or uncomplemented. A minterm is true for exactly one truth table row. Okay, let's check the table. A, B, and minterm true on this row. Zero, zero, one, one. Oops. B, zero, one, zero, one. Okay, so minterm is a product term that contains every input variable exactly once. So A is 1, only one time, B only one time, either complement or either complemented or uncomplemented, which is A0, B0, it will be A0 and B naught, sorry, A naught and B naught, and in this case it will be A naught and B, in this case A and B naught, and in here is just A and B. So this one will be the, what is it, uncomplemented, and this one the complemented. Okay. And for the example here, I think we need to keep the table so we can have a look and see it. So if f is equal 1 on rows 0, 1 and 1, 0, 0, 1 is this one, and 1, 0 is this one, then canonical sum of products is f equal a naught b plus a b naught. Okay. Now let's check product of sums and max terms. A product of sums abbreviation of expressions and together some terms. Its sum term is an OR of variables or their complements. A max term contains every input variable exactly once and is false for exactly one truth table row. Pause is constructed from the rows where the decided function output is 0. Let's check the table. A, B, max term false on this row. 0, 0, 1, 1. 0, 1, 0, 1 contains every input variable exactly 1 and is false for exactly one truth table row. Product of sums constructed from the rows where the decided function output is 0. So a plus b. A max contains every input variable exactly one and is false for exactly one truth table row. So a plus b naught, a naught plus b, and a naught plus b naught, because the truth is here, here, and here, and here. Okay. So for example, the exclusive OR is 0 on rows 0, 0, and 1, 1, which is this one and this one. So canonical product of sums is F equal to A plus B, which is this one, and A naught plus B naught, which is this one. Okay, let's check this one. From a truth table to an expression. So the following function, we're gonna see a table. The following function is true when at least two of the three inputs are true. This is called three inputs majority function. Let's see if I can put the table here. I can put A, B, C, and majority. We have 0, 0, 1, 1, 0, 0, 1, 1. and then we have 0 1 0 1 0 1 0 1. Okay, so what's the majority? In here we have A is 0, B is 0, C is 0, so the majority is 0. A 0, B 0, and C 1. Still A 0, B is 1, but C is again 0, so the majority is 0. If A 0, B is 1, and C 1, in this case the majority is 1. A is 1, 0, 0, 0. A is 1, B is 0, but C is 1 again, so the majority is 1. A is 1, B is 1, C is 0, but the majority is 1. And we have 1, 1, 1, which is majority 1. This one pretty basic, right? Okay. Okay. We can say why Karnaugh maps exist. Karnaugh maps or K map is a visual arrangement of truth table output that makes adjacent Minterms easy to combine and simplify. Boolean algebra can simplify expressions symbolically. A K-map performs the same kind of simplification. Visually, each cell represents one truth table row. But the cells are arranged some neighboring cells differ in exactly one input variable. We already saw that, right? In binary with the gray code. So the column label follows 0 0 0 1 1 1 1 0 rather than the originally binary order, which is 0 0 0 1 1 0 1 1. Okay. So let's see two variable Karnaugh map. So we have A, B, 0, 1. Okay. We have 0 and 1. And we have the Minterm 0 is equal to A naught and B naught. Let's say that the Mr. 1 is equal to A naught B. Actually, let's make it together. Let's put Mr. 0 is equal, Mr. 1 is equal, Mr. 2 is equal, and Mr. 3 is equal. Okay, how this works, basically the A is taking this and the B is taking this. This is how it works. So in this case it will be 0 and 0. So we know already that 0 is A naught and B naught. In the 1 we still have A naught, but now we have B 1. In Mr. 2 now we have A. It's not A naught, right? It's A. But in this case B is not. So A and B not. And 3 we have both of them 1, which is A and B. Okay? Okay, how can we simplify this, for example? Let's see if we can understand it with this example. So let F equal 1 on row 0 0 and 0 1. The two adjacent cells shares A equals 0 while B changes. Therefore, B disappears and the simplified result is f equal a. Okay, row 0, 0 is here, and 0, 1 is here. The two adjacent cells says a is equal to 0, which is correct. A is equal to 0 in here, and in this row a is equal to 0. So it's a naught and a naught. Here, a naught and a naught. While b changes, correct, here is b naught and here is b. Therefore b disappears, and the simplified result is f equal a. The reason why it's that is because the constant we keep it, and the one that changes, this is very abstraction, but for now is what we need to know. We can dispose of. Okay, we will see it. Okay, 3 variable Karnaugh map. A 3 variable K-map has 2 rows. For A and for gray code columns for B, C. The column order is 0, 0, 0, 1, 1, 1, 1, 0. Okay, because in this case it's only only differ by one single digit. Okay. So A, B, C. 0, 0, 0, 1, 1, 1, and 1, 0. And here is 0. Let's put it more at the back. 0 and 1. This is just exactly what we just did, but we just add a different, an extra one. So M0, M1, M3, M2, M4, M5, M7, M6. Okay. we have A and BC for that one, right? So A is 0 equal A is 0, then BC is also 0. That will be am I wrong if I say A not? Maybe B not C not? I need to double check that. Oh, we don't have example, that's great. Let's check the M6. I need examples of that. I'm not 100% sure, and I want to know. Okay. Simple. That was simple. There's the number on it. So if M3 is 0, 1, 1, M5 is 1, 0, 1, 0, 0, 0, right? 1, 0, 0, 1, 0, 1, 1, 1, 1, 0. Because that was the numbers, but now we're doing the majority of it, which is in here. The majority is 0. The majority now 0, 1, 0, 1, majority is 1, 1, 0, 1, majority 1, 0, 1, 1, majority 1, majority 1. Here is the majority 1, 2, and in here it will be 1, 1, 0, which the majority will also be 1. No? Or am I wrong? I was doing 1 in all of them. Okay, but the A is 0. Let's do it all over again. Let's put the same table that they used to do that. The table is M0, M4, M1, M5, M3, M7, M2, and M6. If we make the numbers over here, we start from 0, 0, 0. Here will be 1, 0, 0. Here it's equal 0, 0, 1, 1, 0, 1. 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0. No, this is right, no? So B. So that will be 0, that will be 0, 0, 1, 1, 1, 0, 1, which is 0, 0, 1, 0, 0, 1, 1, 1. Correct, now we got it. Okay. So just an example, if A is 1 and B is equal to 1, but C is equal to 0, because of the majority, it's 1, 1, 0 because of the majority, that's why it up this 1. Basically what it's saying here. But as we said before, the one that doesn't change, we can take it. So if A, B, C, then C is not, plus A, B, C, it will be equal to A, B, C, this C naught, and this C will be like C naught plus C is equal to A, B, 1, which is equal to A, B. That depending on the row, we can do that. For example, let's check here so we make it more clear. Let's check M3 with M7, which M3 is 0, 1, 1. What is 0, 1, 1 here? Okay, and then we have M7, which is 1, 1, 1. What is M7, 1, 1, 1? These two. Okay, so A, this A change because it's 0 and then it's 1, but B remains 1 and C remain 1. So we erase A. We keep B and C. So the result will be B, C. Now it's more clear, right? Okay. The next thing is already logic gates, and introductory to digital circuits. So we will leave this for the next video.